fission and fusion. Got this? Okay. Let's continue. So, you don't need to draw this just yet. But we've seen this equation before. What you have here is uranium-235 and a neutron. And the neutron is fired at the uranium. And what happens is the uranium splits into krypton and barium and 3 neutrons. In fact, that was the first or second question on the homework. Was the first question, was it? Was calculate how much energy is produced. Second question, was it? Yeah. So this is what I mean by fission. Fission is when you break the atom and release energy. Okay, so I just wanted to show you the picture of what this looks like. I think it would be good if you draw the picture. It doesn't need to be as beautiful as this. You can just do a circle here for uranium. Okay, but I think it's good to have a picture for this process. This is an example of fission, where you break the atom to release energy. Okay. No. Yeah. Okay. So, yeah. So the definition, nuclear fission is a nuclear process. It is when an atom splits apart into smaller atoms. The process gives off a lot of energy and is used in nuclear weapons and nuclear reactors. So, very powerful. Oh, you didn't tell me it was a little blurry. Let me fix that. Is it better if it's over here? It's not great either way. Yeah? Okay. No. Okay. Right. So, if you think about it like this, actually, if I go back to the picture here, this one neutron can hit this and make two new atoms, krypton and barium, but 3 neutrons are free. So what if these 3 neutrons hit another uranium, like in the picture here? In this example there's only 2, I don't know what reaction this is, but when this breaks it releases 2 neutrons, and maybe these neutrons hit 2 more atoms, and they break, and they release 2 neutrons, and they hit more, and so on. So this is called a chain reaction, where the first process creates 2 or more, and they create 2 or more, and so on. Each time it splits, you get energy. So each time it releases a neutron, you have energy as well. So this process can be used to make more energy. This is called chain reaction. And I think you can draw this picture too. I don't know which reaction this is. I think in the picture they just put 2 to make it easier to draw. In my example there's 3. But it can be 2, 3, 4, whatever. It doesn't matter. It is.
Our first picture will show here to here.
Yeah.
Same.
The first picture is just the first one up the top.
On top.
Yeah.
The generations are talking about the neutron chain.
The reaction, I guess.
The reaction means the neutron.
I suppose the first generation, yes, it's when the first neutron hits the first atom, and then the second generation is the second neutrons hitting the second row of atoms. I guess. It's not really important. Continue. Okay, so a chain reaction is a reaction in which a heavy isotope like uranium or plutonium splits, and the neutron released by the fission of the atoms strikes and split other heavy atoms, which as a result hit other atoms one after another, so on and so on. The picture is easier to understand than this, but you need to write this down too. So this is the word definition of a chain reaction. got that? Yeah. So, of course, if you think about it, this doesn't always work. If you don't have enough uranium, when the neutron is freed, it can't find the uranium to hit. You know what I mean? So, like, when the neutron is released, it needs to hit another uranium. But if you don't have enough uranium, then it just continues and doesn't hit uranium. So this gives us an idea that we need a minimum amount of uranium for this to work. And this is called the critical mass. And it's how much you need so that the reaction can take place. It's the minimum amount. If the mass is less than the critical mass, then there's not enough freed neutrons to continue the fission process. If the mass is greater than the critical mass, then there are enough freed neutrons to continue the process, greater than or equal to.
Right, I don't understand. The physical mass refers to the...
How much uranium you have. So if you don't have enough uranium, you don't have enough freed neutrons. Without enough freed neutrons, they won't hit into enough uranium to release more.
But there will always be enough free neutrons, because if one neutron hits one uranium, then there will be three.
Yeah, but there needs to be enough uranium. Like if it's low density and you don't have much of it, then the
neutrons will miss.
Yeah, they'll just miss. Yeah, but if you have a lot of uranium densely packed together, then the neutrons would eventually have to hit other uranium atoms on its way out. So you need enough of it. Okay. Waiting for Grace and Amanda?
No.
You're finished?
I'm finished.
Are you sure?
Yeah.
Okay. So, how can you use this to make power? This is a nuclear reactor. Let me explain how it works. Well, let me just check what my next picture is. No. Right. Now, what happens here? You see here, in red, this is your uranium. and what's happening here is the uranium, there's a chain reaction going on. The uranium atoms are breaking apart and releasing energy, and releasing more energy and more energy and more energy. So they're getting very hot. So that's why it's red here. It's very hot in here. So what happens is, let's see, you have cold water. I'm sorry, where is this gone? Here it is, sorry. You have cold water that's pumped into this chamber here. And this it's not water, it's usually something like sodium, not water, something like sodium. And this sodium here gets very, very hot from the uranium. And it gets very hot, and it's then taken out and passed down here. Now you can guess what happens when the water comes in here. When the water here touches the hot pipe, what will happen to it? It'll turn into steam. So the steam gets pushed up here. And then this turns a generator. Do you remember we did generator? So it turns a wheel inside the magnet and it makes electricity. Then the steam comes back down here. And when the steam hits this cold water pipe, cold water goes in. And when the steam hits the cold water, it turns back to liquid water. So cold water goes in, and then the hot water comes out because the steam warms the pipe back up. And then the water can go back in again, and it continues the process.
How to make it hot?
This is the nuclear power plant, nuclear energy. So how can you control it? You have something here called a control rod. So if you have too much heat and too much energy, you put the control rod down, and it blocks some of the released energy, neutrons. If you need more energy, then you just lift it up, and then more reactions take place. So the control rod, it's usually part of something called a moderator, which we'll do in a second. It usually has something like carbon in it, because the carbon can take the neutrons instead of the uranium. So you put the carbon down, and the neutrons hit the carbon instead of more uranium. So carbon is very good at absorbing the neutrons. This is your nuclear power plant. So you see it has all parts of physics in it. It has the AC generator. It has, liquids and gases. It has your heat. It has your nuclear reaction. It's very simple and complicated. You can all understand how it works, but it's very difficult to do. For example, if you have too much uranium here and it gets too hot, then it will explode. So you all know about the problems with the nuclear power plants. One in Japan. Where was it in Japan? No, not the bomb. The power plant that was the problem during the tsunami. Yeah, sorry, that was it. Sorry, sorry. They had a problem. Does anyone remember any other power plants that had problems? Chernobyl. Yeah, very good. Huh? Do you want to tell her?
The Russian power plant it exploded as well, and now it's inhabitable for another 2,000 years.
The area has been damaged. You can't. It's dangerous to live there.
You can't enter because of the radiation.
This was in 1985 or something. It was a long time ago, but still it's a problem. So why or what goes wrong? What's the cause of the problem? Does anyone know actually? Yeah, the uranium here, but what goes wrong what breaks?
The chain reaction.
Yeah, no, but what part of this reactor breaks that causes the problem? Control rod. Yes, the control rod gets stuck in the up position. You can't put it down. So at the control rod you can lift it up and down. So when you want less energy, you put it down, and the control rod comes down. If you want more energy, you lift it up. See, these here move. This is actually connected up to a room, and the people in the room, they can lift the rods up and down. So if they want more energy, they lift the rod up, and then when they want less energy, they push it down. So what happens is, here, you can't see in the picture, but here they continue out, and there's a connection here, like a hole, and the control rod is in the hole, and they want less energy, so they push it down, and then it covers the uranium. So what happens in Japan or in Chernobyl, also I think in what's it called in America, the something islands, the same thing happened. At the place where it connects, it can melt and it gets stuck, so you can't then put it down. So what happens is, this keeps getting hotter and hotter and hotter and hotter until it cracks.
And they can't turn it off.
And you can't turn it off because you need to put the control rod down. So then what happens? Does anyone know what they do in an emergency to try and stop the process?
Move everybody out of the
Yeah, but how can you try and stop it getting hotter?
They try to cool it down using the cold water.
Yeah, what happens is, this cold water, it usually comes from a nearby river or ocean. So in an emergency, what they do is they have a valve here which they can open, and all the cold water from the river or the ocean comes in and fills up the chamber, and it tries to cool this down. So lots of water comes in and then leaves down the bottom. So they just put lots and lots of cold water in to try and cool this down.
Does it work?
No, it does. I mean, this is all you can do. Because if you didn't, it would explode. So it usually does work, except I think in Chernobyl maybe it didn't. I think these are safer to have it near the ocean, like in Japan, because then if there is a problem, you can just let the water fill up the chamber to try and cool it down. Yeah. So they are very dangerous.
Japan throw the water away the ocean.
Say again?
Japan throw the water away the ocean.
Did they put the water in?
No, after they cool it,
Yeah.
cool the temperature down, and they throw the water in the ocean.
They put the water in the ocean after the yeah.
Yeah, or the cool.
No, I think they just release the water back. You see, because the water isn't that dirty afterwards. If you remember, for example, with alpha radiation, it's only it can't get past your skin, so it's only a problem if you drink it. But you don't drink ocean water, so it's not too bad. Like, your choices are have some radiation in the ocean, or the plant explodes. So you have to make a choice, Now, in the exam, they might ask you to draw this or explain some part of it. The part which they usually ask you to explain is the part here with the control rod. So I'll give you the definition of the part that you need for the exam. But I still think it would be nice if you could try to draw this in your book. It doesn't need to be as beautiful as this, but try your best, okay?
Do we have to label it?
Yes, of course.
Is this test in the exam?
In the exam, I think if they were to ask you this, what they might do is leave something missing from the picture, or ask you to explain something in the picture. Now, Amanda, I don't think they will do that, because then that means the person writing the exam has to make this picture. No, seriously. So he hasn't done it in the past, so it makes me think he won't do it in the future.
Can he just,
But it's possible.
he cannot just take a picture of the bill?
No, you're not allowed to do that for NCUK exams. So you would have to draw it by hand. Yeah, finished it, yeah. No, yeah. Yeah? Andy, you got this? Yeah?
Yeah.
Okay. Are you just waiting for her in? Continue?
Yeah.
Yes? Okay. So, in the exam, there's a couple of definitions they like to ask for this reactor. The first one is about the fuel cell here. In the picture, it's uranium. So, nuclear fuel is a material that can be burned by nuclear fission or fusion to derive energy. The most common fuels are uranium-235 and plutonium-239. The actions of mining, refining, purifying, using and cleaning altogether make the nuclear fuel cycle. I don't think you need that definition part for the exam. For the exam, they might ask you what are the common fuels used. So the answer is uranium-235 or plutonium-239. South Korea has nuclear power plants, doesn't it? Or it doesn't?
No idea.
You don't know. Do you know, Sophie? Don't know.
There is no fire even either.
So it has lots of coal and oil power plants.
Yeah.
And what about Malaysia? Does it have nuclear power plants? Hydro. Yeah. China definitely has nuclear power plants. Yeah. We don't know where yet. Oh, I forgot to say actually, sorry, before you write this down. In this picture, you notice that hot water comes out And where does this go?
Ocean?
No, not ocean. No,
Your house.
to your house. So people who live near a power plant like this get free hot water.
But the water is
Also
not
free.
clean.
No, it is clean because the water is in this tank.
Wow.
Yeah, but it's very near the.
Yeah, but this would be concrete and lead. You know, this would be like 1 or 2 meters of concrete.
I see that small pool.
Don't worry, it's clean and it's free.
And if it explode, and the animals become sick like
Yes, yes, and also you might become the Hulk or Superman. Yeah,
Chicken become 6 wings.
that's it. Yeah. And like in The Simpsons, the fish have 3 eyes. You know. Okay, so you just need this much for the exam. Yeah, you got that? Yeah. And the second part, you don't really need it for the exam, it's called the fuel cycle. This is the whole process. So what I mean, the first part is the mining. So this is where you take the uranium from the mine. The second part is the refining. So, you know, the uranium is not ready, it's inside the rocks, so you have to take it out. You have to take the uranium out. The next is purifying. So that just means having no other materials, just clean uranium, nothing else inside of it. Then of course you use it in the power plant. But then finally you have to dispose of it. This means put it away safely. So for example, in France, when they're finished with the fuel cell, they put it inside of concrete at the bottom of the ocean. They bury it underground.
The ocean will be polluted.
Well, this is the problem they're having now. Yes, because the concrete has cracked. So. The last step here, disposing. That means when you're finished with the uranium, what do you do with it? You can't just put it in the bin. So what they do in France is they bury it under the ocean.
Yeah.
How did it crack? If there's nothing disturbing in the ocean, is there a cracking?
I don't know, the concrete cracked for whatever reason. Maybe it didn't behave like it thought it would on the ocean floor. But that's not really done nowadays. So there are other places where they can safely dispose of it in a special facility. So for example, in the UK there's a power plant, disposal plant in Sellafield, where the used nuclear fuel is taken there and it's recycled. I don't know how they recycle it, and I don't know what they do when they recycle it, but they recycle it at special plants in the UK.
Then what do they make?
I don't know. I have to find out. They recycle it? and it's used for something else. I'm not sure what else. Maybe they recycle it to use it, in smoke alarms or whatever. I don't know. Probably not smoke alarms, but they recycle it and they reuse it some way. I'm not sure how. I'm not sure how they clean it up. I imagine it's very expensive and very difficult to do. It's much easier just to dump it in the ocean. But you can't really do that anymore. Health and safety. Yeah. Ireland, of course, has no nuclear power plants, and I don't really think they're suitable for every country. So a country like China, growing population, big population, they would need it. Or places like France and Germany and America, yes. But smaller places like Malaysia, like Ireland, I don't think it's a good thing because they're too expensive. And the other problem is you need a very advanced energy grid. In Ireland, our energy grid, you know what I mean by energy grid? How the energy gets to the homes. In Ireland, our energy grid is very old. Very, very old. I don't think it could handle such a plant. And anyways, the number one reason I think not to use these is they're too expensive. I don't think it's the future. Okay, and all of course also they're dangerous.
What does Ireland use to mill?
There's not so much. Mostly coal and oil imported. Some hydro, but not much. Ireland's very bad for renewable energy. Very, very bad. I think Ireland is the worst country in Europe for renewable energy. It uses too much coal and oil. So Ireland gets a 0 out of 10 for green energy. Very, very bad. So yeah. Germany is very good for green energy, I think, Germany. Okay, so this thing here, moderator, this is what's at the end of the control rod. It's what takes the neutrons. Great. A neutron moderator, it reduces the neutrons. You have, yeah? You remember you have the control rod. So at the bottom of, like here, at the bottom of the control rod is what's called the moderator. This is what takes the neutrons when you have too many. So its full name is a neutron moderator, and it reduces the neutron speed. Now I don't think I say it. No, I don't say it here. But usually, what is used is carbon, graphite, like in your pencil.
Picture also the bottom of control rod is reactor.
What's the difference control rod and reactor?
Yeah, reactor.
Same.
It looks the same, does it? Let me try and help. Come on. Wait, no, too far. It's after this, isn't it? Yeah. So, the picture is bad, yes. This reactor core is actually the name of the whole thing here. And this is the control rods, and these red ones are the fuel rods. The moderator is a material at the end of the control rod, like carbon. What's not great about this picture is these control rods really go out of the reactor inside of a room where people can pull them up and down.
What if they save it?
Yeah, don't be doing that, please. Right. This is really the key part of the definition. It reduces the speed of the neutrons. So this is the most important part of the definition. It reduces the speed of the neutrons. So usually what happens is the neutrons are going too fast and you need a moderator to slow them down. Naturally the neutrons want to go very fast. The moderator slows them down, like a speed bump. Yep. No. We're just waiting for you? Yes. Okay. So control rods are used to control the rate of fission, the uranium plutonium. Now, the control rods, well, we talked about them already. They control the rate of fission. So when you want more, you lift the control rod, and when you want less, you lower the control rods. And they're usually made of things like, I know I said carbon, I think carbon is one of them, but we can have boron, silver, I didn't list carbon here. I think carbon is one of them. But I think maybe boron is more common. I don't know. You don't really need to know that for the exam. You just need to know it's made of something like this, boron or silver or something. I don't think any is made of silver. That sounds too expensive. I don't know. Anyways, the key part I need for the exam is basically this, that they're used to control the rate of fission. So you want more, you raise them. You want less, you lower them. So if you could just get this sentence, just this sentence. Control rods are used in the reactor to control the fission rate of uranium and plutonium. There's not much of a difference. The only difference is the control rod comes out of the reactor into the room, whereas the moderator is always inside the reactor.
So basically the moderator is the bottom part of the control rod.
Yeah, really it is. But sometimes okay, to put it this way, the control rod you can move up and down, and there's usually a material at the end of the control rod, like a moderator material, like carbon or boron. But there's also moderator material in the reactor all the time. You know, it's like there's permanent moderators, which are always in the reactor, and then there's ones you can adjust, you know. So, I guess moderator is almost like the name of the material that you use to reduce the neutrons, and control rod is actually the name of the rod that you move. The difference is, what would be a comparable example? I don't know, it's like when you're driving the car, you know, your foot is on the accelerator. So yeah, you put your foot down for more and lift it up for less. But of course, inside the engine, even if you don't put your foot down, the engine is still turning, so there's still fuel going inside of it. In the nuclear reactor, there is some moderator material always in the reactor, and if you want more or less, you just change a little bit of it, you know. That is way more than what you need for the exam. In the exam, they just want you to say, what does a moderator do? And what a moderator does is it reduces the speed of the neutrons. And then another question might be, how can you control it? You control it by using a control rod. You want more, you lift the rod. You want less energy, you drop the rod. I find most pictures on Google, they don't clearly show the difference between the moderator and the control rod. And I want to get a better picture. I keep looking every year for a better picture. The picture I have is the best one I could find. But that's more than what you need for the exam. I also consider that as well, but this picture looks so beautiful, I don't want to. Right.
And finally, the definition of this chapter is very important.
There's 4 definitions really important. Moderator, control rod, 5 definitions. Chain reaction, fission, and there's one more definition we haven't done yet, which is important. And that's the next slide. So, for this lesson, it's really about the definitions. Fusion, fission, chain reaction, moderator, control rod. Now, did you do these words with Lorraine? Deuterium.
No.
You don't know deuterium? I'll tell you deuterium. And tritinium.
We do neutron and energy.
Yeah.
Helium with fluorine.
I'll tell you what these are. Deuterium is actually H2. It's hydrogen 2. It's an isotope of hydrogen. I think you learned in chemistry how many isotopes of hydrogen are there?
1, 2, and 3.
There's 3, isn't there? So actually 2 and 3 have special names because they're important. This is actually H2. It has 1 proton and 1 neutron. This is H3. It has 1 proton and 2 neutrons. So these are both hydrogen isotopes. Okay? Now what happens here? You put these 2 together, they try to stick, and then what you get at the end is this. You get helium and a neutron. Here there are 2 protons, these 2 protons, and here there are 2 neutrons. 2 neutrons here, but you see there's 1 neutron free. Now when you calculate the mass here and calculate the mass here, which is bigger? The mass on the left is bigger because some of the mass here was changed into energy. So this is called fusion, when you take 2 atoms and smash them into 1. It's the opposite of fission, where you take 1 atom and split it into 2. Okay? So this picture, if you can draw this please, this is an example of fusion. Continue. Continue. Yes? Amanda? Yeah. Nuclear fusion is the process of making a single heavy nucleus from two lighter nuclei. This process is called the nuclear reaction. It releases a large amount of energy. Okay. Oops.
Does fusion release more energy than fission?
I wouldn't say really it's more. I'd say it's about the same. We could actually calculate it because we have the diagrams. We just need the mass of H2, the mass of H3, the mass of helium, the mass of neutron, and we could actually easily calculate how much energy per reaction. Part of the homework was the energy released from the neutron being fired into the uranium. So you could actually do the same thing here and compare it. Now, this is important about fusion. Are you listening? Listen. This is important about fusion. Fusion reactors are 100% safe. There cannot be an accident with them, because the way this process works is you take the H2 and the H3 and you fire them together. So you control the process. If something went wrong, all that would happen is the hydrogen 2 and the hydrogen 3 wouldn't make helium. If something went wrong, the worst thing that happens is just the hydrogen just releases. But that's okay. It's just hydrogen. It's not like it's going to, explode in a nuclear explosion. This process cannot cause a nuclear explosion, unlike the last process. So it's 100% safe. But no power plant uses this process because it's a very difficult process to do. It's very, very difficult to have the H2 and the H3 fire together and stick them together. So right now, I think the first time this was tried, it only lasted about 2 seconds, and then it turned off. I think at the moment maybe you can get it last about maybe 15 minutes, and then the process stops because it's so difficult to keep it going. So you might wonder, how do they stick the two together? So what they do is they have H2 and H3, and they have it in inside the gas. Now if you look at the picture here, what charge is H2? It's positive. So if you remember from, oh my goodness, which one is it, left or right? The right hand grip rule. That when you have a positive charge, there's a magnetic field around it. So if you have a magnetic field around this, you can try to control it. So what they do is they try to make it into a ball shape using the magnets around it. So it's a gas and they keep it into a ball shape. Then what they do is they fire lasers into the center, and it makes it very hot. So when it gets very hot, what happens to the H2 and the H3? They start to move faster. And if they move fast enough, the H2 will hit a H3, and just like in my picture, they'll stick together and they make helium. And the energy is released as heat. And the heat energy here will be 10 times more than the energy of the laser used to make it hot. So for example, if you use 1 joule of laser energy to make this hot, the heat that is made is 10 joules. In fact, this is exactly what happens in the sun. So if you think about our sun, it's hydrogen and helium. And what's happening is the hydrogen is turning into helium and releasing heat. But of course, there's no lasers making it hot. So what is the process that makes the hydrogen and the helium stick together? Yeah, but what?
I don't know.
It's the gravity of the sun. So what's happening is here, like you said, the mass is so big, it pulls the hydrogen together and it sticks and forms helium, and then that releases the heat. So if the sun is too small, this process won't happen. So it needs to be a minimum size. Now, there's actually many other things happening, but it's just to give you a simple idea. So what you actually do in the power plant is you make a small sun in the middle of the room, and it glows and the heat comes out. But you might then ask, well, how do you get the heat? It's too hot to put the water near it. So then what they do is they put something like lithium. You know lithium? Yeah? They put lithium around it. So the heat makes the lithium hot, and then you have your water pipes going by. So the helium and hydrogen are too hot, but they heat the lithium, and the lithium then heats the water. Okay? So this is what the future will look like for energy, I think.
So you can get it right.
Yeah, well, Europe, Japan and China, I think, are working on making the first fusion power plant. I can't remember what it's called. I can't remember. Something like the Joint European Japanese, I don't remember. It's something, I don't remember. They're working on making a fusion power plant. The good thing is this is completely clean, because what do you get at the end? What do you get at the end? Helium, which you just put into a balloon at children's parties. You know, it's completely clean. There's no waste, there's no radiation, there's no dirt from it. So maybe in 20 years, maybe in 50 years, this will be normal in every country. 50 years, I would hope maybe you're still alive, you know. Okay, so the good thing here now, there isn't homework here for this because they're definitions, which means next time we have no homework to do, so we should finish, I think, these two next time, which means on Monday then we'll finish, and we can start our revision on Tuesday, isn't it? Yes? This makes you happy?
Yes.
No. Yes. It's very exciting to be nearly finished, isn't it?